All right, everybody, let's get started. I'm going to go through this real quick. I think most of you heard this last time, but I'll go through it pretty quick. I wanted to go through the solution to the homework. So real quick, you all did very well. I don't think there's really a whole lot to say. So you've been given, for problem one, you were given this building, you were given a dead load and an unreduced live load, and you needed to determine the responses of some of the elements. Excuse me. Particularly one of these interior beams up here, this girder, and that column. So, all right. And then you also were given a series of locations to determine design loads and what have you, specifically ground, snow, base wind speeds, and seismic accelerations. So for problem one, given that dead load and that live load, the first thing that I did was go through the tributary area and live load reduction calcs. For that beam, the tributary width is just 1/4 of that, or of the base spacing, because the beams were at quarter points, so about 11.25 feet. The beam's 30 foot long, and since it's a beam, its live load element factor is 2. So you can calculate its tributary area as just that width times the beam length, comes out to about 337 square feet. And from there you can do live load reduction, so that 70 PSF turns into about 58 PSF. Factor it to determine your factored load, distribute that across the tributary width to obtain something we can handle, a uniformly distributed load on a simply supported beam. And from that you can calculate the moment pretty easily. Now, you don't need to for this part. I went ahead and calculated the support reactions at each end, comes out to about 22.7 kips. You'll see why here in a second. All right, so that's part A, about 170 foot kips. Part B, you needed to compute the maximum shear on that interior girder by distributing the reactions. So when you look at the floor frame, it looks like you need to do part A all over again, because you need to do the tributary area, the live load reduction, and all of that, and then you have to do the analysis again. But I was a little crafty on the development of the problem. If you just look at one of those floor beams in that inner bay, the tributary width is different and the span length is different, but because the live load element factor and ultimately the tributary area are identical, because these two numbers are the same as the numbers up here, we can make a few observations. Because those two numbers are the same, the live load reduction is going to be the same. Because the live load reduction is going to be the same, we're going to obtain the same factored load. And because we have the same tributary area, it's the same support reaction. So if we only have one floor beam framing in on each end, we don't have two, we don't have a floor beam over here and a floor beam over there, we just have the one, this is our analysis model. And we need to determine our factored maximum shear, which just looking at what the shear diagram would look like, it's going to be the support reactions. So just sum up all that load, cut it in half to get a reaction on each end, comes out to about 34 kips. Everybody good? Part C, you just need to calculate the area of the tributary section for that given column. Pretty straightforward. There's 3 bays, just half the spacing this way, half the spacing that way. There's a live load element factor for this of 4. Do your reduction, factor your loads. Just take the pressure load times the area to get the load for a single story, 4 stories, multiply it by 4. That gives you a base column reaction of about 390 kips. Everybody good? Last part, I didn't really go into it. I sort of just summarized because it's just, plugging and chugging into online design tools. But grounds, let's see, or start off with base wind speeds. Here at Marshall, the base wind speed is 115 miles per hour, as it is in most of the interior portion of the United States. When we're dealing with coastal regions, like out in Miami, wind speeds get larger because of hurricane force winds. Gets us up to 180 miles per hour. That's wind. Snow loads here at Marshall, the design ground snow load's 20 PSF. Up at Harvard, it's a little farther north. Snow load gets a little larger, it's 40 PSF. Seismic accelerations, we've got Marshall's seismic accelerations and then the ones out at UCLA. Those are larger, obviously, because we're in a more significant hot spot for earthquakes. Just a real quick explanation of what these values mean, keep in mind we're talking about the fraction of acceleration due to gravity. Like if any of these values were 1, it would be like taking the building and literally picking it up and standing it like this and designing the whole building as a cantilevered beam. That's a gravity of 1, okay? So 0.149, that's about 14.9% of gravity and what have you acting this way. Now, just so you have an understanding of what these values mean, the first two, the SS and the S1, stand for seismic accelerations at short periods and at 1-second periods. And kind of the quick way of describing that is short accelerations, or if the a sudden change in acceleration in an earthquake, like a jolt, if you will, that's a short period acceleration. The 1-second duration is more for a sustained earthquake, like if an earthquake lasts a fair amount of time. So these accelerations will tend to be smaller than the short periods. Make sense? Now that's for your base accelerations that you get from the map. To go from here to here, your modified short period and your modified 1-second durations, those are a function of the soil conditions. You'll notice different adjustments from here to here at UCLA than you have here at Marshall, and it has nothing to do with the location. It has to do with these site classes. It's a different, we chose a different site class for UCLA than we did at Marshall, so we get different adjustments. How do we get from here to here? Our modified accelerations to our design accelerations, we just multiply them by 2/3. That comes from design or code specifying bodies and engineering judgment, basically saying we really only need to use about 2/3 of that acceleration for the purposes of design. Everybody good? Yes, sir. Yeah, I know I never said that. It depends. It's not a really straightforward calculation. It's really more of a function of the density of snow, and that's a little bit of an involved calc. You want a rough estimate around here. We're talking about 7 to 8 inches around here. One point I will make is we pretty much exceeded that here a couple weeks ago, or at least came close. What happens is, keep in mind, when we look up those snow loads, we're looking them up based on recurrence intervals of 50 years. So because of that, when the next edition of the spec comes out, it may not be 20 PSF, it might be 21, because the last couple winters we have bumped the averages up a little bit. That's very possible. That's one of the reasons why these specs come out every so often, is for things like environmental loading, like snow and wind and what have you. The wind stuff doesn't really change a lot. The snow, that might. And it's just a function of data collection. No, yeah, I mean, and I mean, there's, if that involved recent construction, then there's probably going to be some engineers who have to, defend what they've done. And if they followed the specification properly, then you can't really fault the engineer. And one thing I'll say about this, next time, and I know this doesn't affect you all because you're in concrete, but next time in steel design, we're going to talk about an incident called the Hyatt Regency walkway collapse. How many of you have heard of that? Anybody heard of the Hyatt Regency collapse? No. It was this suspended walkway in a Hyatt Regency in Kansas City. To date, it is one of the worst structural failures in U.S. history, where a structure failed under its design load. It was designed for that load, and it failed anyways. Now, in steel design, we'll talk about why. I mean, in that incident, it was over 100 people died, so it's a big deal. But, let me say this, and it'll go into the reason why I brought it up. If you design according to ASC 7 and you follow those procedures properly, and then the loads just happen to exceed what were in the specification, it's really not your fault as an engineer, because we design based off of a probabilistic point of view, and if the loads exceed that, well, I mean, it is what it is. But that's one of the reasons why codes change. I mean, to be honest, 95% of what we know in the world of structural engineering came from things failing, not from things behaving successfully. So it is what it is. It sucks, but that's just the nature of things. Everybody good? Well, that's where the load combos come into play. What are you doing with that load? You're taking it and multiplying it by 1.6, or when you do 1.2 times the dead plus 1.6 times the live, or 1.6 times the snow. That's what you're doing. You're taking into account that factor of safety. Okay. What happens is, but keep in mind, when we select a design snow load in Huntington, West Virginia of 20 PSF, we're doing that based off of the data that we have. If we get more data, that load can change. And maybe in 2017 or 2016 or when they decide to come out with a new ASC 710, that load might be different. It depends. Keep in mind what you're, and there's a lot of statistics that goes into this, but what you're using is a statistically representative average, okay? If you have a storm, that, produces an excessive amount of additional snow, that's probably going to throw the average off for the whole data set a little bit. But again, there's a lot of statistics that go into this. I could go on into the how they actually, do the reliability calcs and come up with these values, but that's way beyond what we're talking about here. I'll suffice it to say that if you get, if you get snow events that are very significant and go above and beyond, they can throw your data set. Just take a look at snow load maps and snow load values from one edition to the next. They change. And they change because we have more data. More data gives us a better picture of what we're looking at. Does that help out? This is good stuff. Seriously, this is good stuff. Anybody have any other questions?
So you're not. If there's like a serious change between editions, will they go back and not reinforce buildings? But like if the snow load drastically changes, do you think they would go back and reinforce them?
Well, I'll tell you a little story that goes into that. There's a story that we actually didn't talk about this semester, but you might actually talk about it in another class. Like if you all take senior seminar, you all talk about ethics and whatnot in that? Do you all mention the city court building in that class? Do you all mention the Ford Pinto? Okay, those are two sort of polar opposite cases. I'll talk a little bit about the city court building. So how many of you have been to New York City, or specifically Manhattan? Okay. If you Google the city court building, here I'll pull an image. I'll pull an image because I think this is worth discussing. It's a really strange building. Right off the bat, it probably looks a little weird. Okay, so this is the city court building in the middle of Manhattan. And the main supporting columns are a little different than what you would expect. They're not on the corners of the building, they're in the center of the building. Now you might go, why make things complicated? And I'll tell you exactly why. It's this right here. Okay, do you know what this is? Does anybody know what this is? Okay, this is a church right here on this property. And basically what happened is when they wanted to construct the facility, the church, who owned the majority of that land, basically said, look, you can put whatever you want on this lot, but the church ain't going anywhere. It's staying where it is. So how do you erect a building in that confined space while leaving the church intact? You put the columns in the middle of the walls as opposed to the corners. Okay? So it was a really, nifty design. And the structural engineer who was responsible for the design of the building was a guy named Bill LeMessurier. And LeMessurier is sort of was regarded and still is as kind of like a Michael Jordan of structural engineers of tall buildings. Like this guy knew what he was doing, and he was one of the few people on the planet that did know what he was doing. So the building's done. Fast forward about, I don't remember the exact time frame. I want to say it was about 10 years. And there's this graduate student at Stanford, I believe, and she's doing a master's project for her degree, and she's got to do this analysis of the building. And she decides to do the city court building. And she's sitting here in her, grad student cubicle space doing this analysis. And she finds that if wind strikes the building at quartering points, that and with significant force, that the building is going to fall down. Now, we're talking about this, lone grad student off in space critiquing a design of one of the preeminent structural engineers on the planet. So first thing she does is go to her advisor and say, am I right about this? Because this is, one hell of a claim to make. And sure enough, she was. So they essentially picked up the phone, called Bill LeMessurier, told him what they found, sent him all their stuff, and turns out they were right. And the reason why was because the bracing connections on the building were meant to be designed or constructed one way, and they weren't. They were constructed in a different fashion. Hurricane season was coming, and they're like, well, we got to do something. So first off, it's heralded as one of the most ethical behaviors on the part of an engineer, because LeMessurier sort of stood up and said, yeah, there's an error here, and owned it, kept his license and everything. I mean, suffered, some legal consequences as a result, but in the end, kept his license and was found to be, justified. And in the end, designed and helped oversee the retrofit of the structure. And overnight, they took all the bracing elements and were like welding these cover plates on the end of it, in the middle of the night to not freak out the people that were in the building, like, oh God, the building's falling down. But in the end, they arrested the problem, and everything was fine. So long way around to answer your question. Yeah, if there's some serious issues coming down the line, some serious load events, and we're talking about fairly significant structures, then yeah, that can happen. So I guess to summarize and to answer your question, in the right scenario, yeah, that does happen. Yes, that does. This is good stuff. I like talking about this. I was just getting ready to say that was an episode on numbers. Yeah, because I remember watching that episode. I was like, they stole this. What's that? What, that the person who owned the building had like killed somebody or something on That's where it goes from real life to CBS. All right. Yes. The what? The what? Oh, the Ford Pinto. That's sort of the exact opposite end of the spectrum. There was the construction of and the design of the Ford Pinto back in the 1970s. This is a really good ethical case study because it really brings up some serious questions. And I don't remember the technical details because I'm not a mechanical engineer and not really into that world. But the long and short of it is, and I believe it was in 1972 when the vehicle was being manufactured, there was a design assessment done on, I believe it was like a floor plate under the gas tank, or somewhere between the gas tank and the driver's seat. There was this like structural plate that they were going to affix to the bottom of the car, and they did a benefit cost analysis to see whether or not they should install that plate. And what happened was, in their benefit cost analysis, they quantified how much lawsuit settlements that they would have to pay out if people died as a result of the crash. So they were essentially placing a dollar value on the life of a human being. And in their benefit cost analysis, they found it was cheaper for them to not install the plate. Yeah. So then, yeah, and Ford Pintos, apparently, from what I understand, because again, I don't remember the details, but they had sort of a way of exploding. Yeah, yeah, exact opposite end of the spectrum. I mean, yeah. So but that's like a very old case study, and if you ever, I know that some institutions that offer engineering degrees, they actually make their students take engineering ethics. And I would love to teach that class. I would love to teach it because it would be, I mean, we talk about some really interesting stuff, but, you know, another story for another day. Random stuff. I know engineering ethics sounds boring, but was the last 10 minutes boring? And I mean, that's the kind of stuff you talk about, so. Except now, back to rebar and. All right. Where did we leave off? Somewhere with, you know, design and what have you. Okay. We were talking about the concepts of design, and let's sort of get back into the swing of things. So if you're missing any handouts, they're over here. I've got one handout for you today to make your lives a little easier in terms of beam design. But I want to kind of revisit my discussion, and some of the stuff that we're going to see here in this discussion, I think, is going to be clarified a little bit with a handout that I'm going to give you all today. So real quick, we discussed the concept of designing an economical beam. What defines economy in a beam? And for us, we're really looking at efficiency. You know, do we just keep throwing rebar into the beam to make it stronger? Or is there some level of sophistication that we can throw into the selection of how much rebar needs to go on that beam? How deep does it need to be? And what have you. So we started off looking at our resistance factor, and then I introduced this term called a reinforcement ratio, which is really going to be a nice tool for us for design, because given the at least assumed or appropriate dimensions of this beam, or an assumed reinforcement ratio, that is the seed upon which we can design the remainder of the beam. Now, I started off by saying, using this term, this definition for a reinforcement ratio, I can rewrite what the stress block looks like, what the depth of the stress block looks like, and what Mn looks like as a function of really three things. One of them being material characteristics like Fy and F sub c prime, not, you know, that tough to assume right at the beginning. A function of this term BD squared, which BD squared is a term that really defines what the shape of the beam is, how wide it is and how deep it is, and this reinforcement ratio. Now we look at what does the moment capacity look like if the reinforcement ratio goes up, and it seems to make sense that I throw more rebar into the beam, it gets stronger. Seems like a reasonable assumption, and that's correct. But that doesn't mean it gets safer, because it's all about its mode of failure. Piling rebar into a beam does not mean it fails in a safe fashion. If you pile a lot of rebar in that beam, those bars are not able to achieve those large strains that we like, and they fail quick. So this, you know, far into the curve, all the way here on the right, you know, looks like we got a lot of capacity, but we're having to reduce it a lot to account for the fact that it's going to crush. Lower amounts of rebar, on the other hand, that's kind of nice, because those lower amounts of rebar, they yield. They're able to achieve those large strains, and that's kind of what we like. Everybody good? So if we could keep our beam in this range when it comes to design, we'd really like that. That'd be nice. It'd be an efficient and safe design. Excuse me. So the nice thing is that given a rho value, a reinforcement ratio, I can determine how big my beam needs to be. This term represents the shape of the beam, and it is a function of the applied moment, material characteristics, and rho. All I need is rho, okay? Now, rho, again, is defined as the area of steel divided by what I'll call the effective area of the concrete, B times D. Now, we can, when we're in design mode, we can actually select rho using two different philosophies. And I think this was probably where things got a little confusing last time, so I'll kind of explain a little bit with this handout I've got. One of the ones that we're going to use a majority in this class, like this is the one I really want you all to use because it's really, really simple, is for design purposes, I want us to assume a row of 0.18 times the square root of FC, or times FC prime over Fy. No square root. Sorry about that. The reason why, that comes from an older edition of the spec, and it was meant for making sure you had proper reinforcement for deflection checks. Just because it's old doesn't mean it doesn't work very well. And for design, from a design standpoint, it actually works pretty well. Okay? So what we're going to do for the majority of our problems is use this for design. Now you can also select a reinforcement ratio such that you achieve a target strain value in the steel. Like you say, okay, I want the steel to yield, what's the required reinforcement? Or I want the steel to reach a strain of 0.005, what's the target reinforcement, and what have you. And you can do that as well. I'll show you how you do that. You start off by looking at your strain profile, and then based off of that linear strain profile, define an expression for C over D. Then what you say is, looking at your stress block and looking at your expression of capacity, I can also write a similar expression for C over D. They must be equal to one another, so now I can define a new expression for rho as a function of what? Material characteristics and the strain of the steel. Now let me pass something out to you all so that you all can see what I'm talking about. Yes. Yes. I have a particular reason why for showing you this now. We're not really going to use it too much now. I just want to plant the concept seed into your head right now. Okay. So if you look at, let's look at this equation. So what do you need in this equation to calculate a reinforcement ratio? You need an FC prime, you need Fy, you need beta 1, and you need a target strain. Now, that guide that we're looking at, I actually want you to look at the back of it. Zoom out a little bit. So you start off by choosing your Fy and choosing your FC prime, and then based on a desired strain condition, you can determine a required reinforcement ratio. I'm just going to be frank, we're not really going to use that too much right now. We're really going to stick with the 0.18. I did want to plant this seed into your head, the idea that we would evaluate the beam at different strain levels, because later on, we're not just going to look at beams, we're going to take a beam that's bending and also apply an axial load to it. And applying that axial load to it will create a beam column. And in order to assess beam columns, we use interaction diagrams, and we'll talk about that later. But an interaction diagram evaluates the column at different strain conditions. So this is the required rho when the strain is 0.004, when the strain is 0.005. Balanced is when the strain reaches yield, okay? Minimum based off of that minimum steel requirement for bending. So just so you have that information. Again, we're really mostly going to use what's on the front of that sheet of paper. So just so you have food for thought for later. Okay, everybody good? All right, so I want to walk through this procedure very carefully and very slowly. So number one, okay, I'm going to outline what is the procedure for designing a beam when you don't know what the beam looks like, you don't know how much steel's in the beam, you got to start somewhere. So we're going to start off, the first thing we need to do is compute the factored moments on that beam, okay? So we need to make an assumption as to what the beam looks like, we need to assume a self-weight of the beam. Now we can assume that, or we can determine that by taking a wild guess as to how tall that beam is, the height of that beam, then making a little bit of a guess as to the width of the beam. Again, they're guesses. We just need a value to start with. Once we get that, assume a phi value. We take mu and divide it by phi, because think, for design purposes, we'd say phi mn has to be greater than or equal to mu. So mn would have to be greater than or equal to mu over phi. So we at least need that much nominal moment capacity. Once we determine how much nominal moment capacity we need, or assume a rho value for design. That's a really good one. You can use other ones if you'd like. That's a really good one now. Oh, excuse me. Calculate BD squared, which is the beam proportions that we're going to use for design. Use a reasonable B over D ratio, which tends to be anywhere from about like 1.5 to 2.5, somewhere around there is a good one. Then we'll use that and choose B over D, B and D values for a trial section. When you're selecting beam dimensions, do not tell a contractor that you want a reinforced concrete beam that is 14.623 inches wide. Just make it 15 inches. Keep it simple, all right? Make sense? All right. Based on your reinforcement ratio, and now that you've got some dimensions, calculate the required area of steel. Choose a reinforcement pattern that meets minimum beam width requirements. We'll talk about that here in a second. But before we do, let's go back to this and look at the front of the sheet. Okay? So this first table up here tells you how many square inches are within a number of bars. So if I'm looking at number 7 bars, and I've got 5 of them, that's 3.01 square inches of steel. Does everybody see that? That'll help us out when we're selecting patterns for reinforcement. Okay? Now, we will use, when we design beams, this upper table and this bottom table pretty regularly. And let me show you what's going on with the bottom table. Okay. When you're designing a beam, you've got to make sure that you're selecting a reinforcement pattern that makes sense. See, you might be able to shave a couple square inches of steel off of your beam if you have a beam and you say, well, I can just throw like 20 number 3s into that beam, and that'll work out. Well, that's great, but the problem is, how do you fit 20 number 3s into a beam that's only 12 inches wide? You don't. Okay? There's this concept in reinforced concrete design called cover. Okay? In other words, cover is a dimension that defines the distance between the face of the rebar and the face of the concrete. More cover is required for different conditions. To give you kind of an idea, if I'm talking about the interior column in a building, I might require 1.5 inches of cover. In other words, if I've got a piece of rebar, there's got to be at least 1.5 inches of concrete around that rebar to protect it from the weather and corrosion and things like that. Now that's for the interior column of a building. If I was talking about the pier on a bridge that's in the middle of the ocean or something, I might need 4 or 5 inches of cover. Because that system is exposed to salt water, the cover requirements are far more stringent. Does that make sense? So cover requirements are a function of what you're looking at. Okay, so that's what cover is. It's a protective layer of concrete around a given piece of reinforcement. For interior columns and beams in a pretty regular building, ACI requires a cover of 1.5 inches. So if you start talking about reinforcement patterns, hi.
Those guys who showed up.
Okay.
Talking about scholarship.
Okay, are they here now?
They're here, but I
10:40. Okay. That gives me another 4 minutes.
You got a fast forward button, right?
I'm actually, it's,
Just give them a note. They don't need instruction.
yeah,
This is concrete.
concrete design. This stuff doesn't matter.
Anyway, right? Not important anyway. You want to play with dirt.
Oh, okay, where was I? Oh. All right, real quick, let me go through this, and then we'll tackle our design problem next time. But, okay, so we're dealing with this beam, okay, and this is just to give you kind of an idea of how you would compute beam widths, okay? So you start off and you say, okay, here's a beam, okay? I got to take off 1.5 inches off each end to account for the cover requirements on the end. I then got to take off 3/8 of an inch to account for this stirrup, assuming that my little hoop stirrup there is a number 3 that we would use to tie the cage together. I've then got these bars inside, let's say they're number 10, so I've got to compute those bar diameters as in addition to the required space between them. So because of that, what I'm getting at is this. I'm saying that based on a given reinforcement selection, if you assume something like 1.5 inches of cover and number 3 stirrups, you can only take so many bars and fit them within so much of a beam width. Do you see what I mean? So if I look at this table down below, okay, minimum web width for beams with inside exposure. So we're assuming, you know, that 1.5 inches of cover, and we're assuming 1.5 inches of cover and assuming number 3 stirrups. So if I had a beam that had 5 number 7s in it right here, I'm saying that in order to fit those bars inside that beam, meet cover requirements, as well as appropriate spacing between those bars, that beam has to be at least 12.8 inches wide. So the idea is if you're in beam design mode and you say, okay, I calculated that I need a 12-inch wide beam, and 5 number 7s would work great, but I don't have enough space to put those 5 number 7s in there. I got to do something differently. Does that make sense? Okay, that's something I really wanted to clear up so that you understood what these two tables were, and we're going to use those in very significant detail next time. Let me go back to the PowerPoint real quick. All right, so I want to take a little bit of stock and for you all to absorb what's going on this example. So we have a beam that's 22 foot long. We're going to subject this beam to 1 kip per foot in addition to its self-weight. So the beam is going to have some self-weight, and then it's going to have a superimposed dead load of about 1 kip per foot. It's also going to be subjected to a live load that's 2 kips per foot. For the purposes of this problem, we'll say it's already been reduced. And I want to design the beam employing 4 KSI concrete, 60 KSI steel, normal weight concrete, and we'll use an approximate D over B ratio of about 1.5. Okay? Now, what we're going to do is we're going to go through this example next time start to finish, but then what we're also going to do is I'll open up a little Excel sheet and say, how does FC prime really affect the design? How does the yield strength of the steel really affect the design? So that you all have a little bit of an understanding of the sensitivity of some of these parameters, so that when you're in design mode and you have a beam that doesn't work, do I make it wider? Do I really need to up the strength of the concrete? How much does that matter? How much does the area of steel requirement, how much does that matter? We'll talk about that next time. All right, so is everybody good? Okay, all right. What I'm going to do is I'm going to stop the recording. I'll see if these guys are out here, and then you all hang out there. Let me explain real quick. We've got some folks from the Contractors Association of West Virginia who'd like to talk to you about scholarship opportunities, i.e., if you would like money. I think students tend to enjoy money. So they're going to talk. What's that?
Common misconception.
All right, so let me go ahead and stop the recording, and we'll see if they're out there. All right.